Welcome to the OpenMined AMA, Ask Me Anything. OpenMined is an open source community focused on making the world more privacy preserving by lowering the barrier to entry the private AI technologies. In this AMA interview, you'll have the opportunities to ask questions of privacy experts from the OpenMined community. My name is Amel Sellami, and I'll be your host. I'm from Sfax, Tunisia, and I'm an AI engineer working at a company named Instadi. First, we're going to have like an amazing guest today. Her name is Fatemehsadat. So Fatma is a second-year CS PhD student at US San Diego and winner of the National Center for Women IT Aspiration in Computing Collegiate Award in 2020. She received her BS Computer Engineering with honors from Sharif University of Technology. In 2018, she works at the intersection of machine learning, system privacy, and OS 20 conference and at the 2019 SPN. Hi, Fatma.
Hi, thank you so much for having me here. It's really a pleasure. I'm so happy and honored to be here.
Thank you for joining us. So today our agenda will have like a small demo or a small presentation. If you have any questions, please do post them in the comments, and then later Fatma will answer them. And after the demo, we'll have the Q&A part, which is the AMA part. Thank you.
Awesome. So I'm going to be sharing my screen right now.
Okay, cool.
Can you see it?
Yes.
Okay, awesome. So I'm going to start by answering the question that why is privacy so important, especially like right now when we're using machine learning so much, and why do we care for it in the context of machine learning? So as we can see here and also around us, we're using so many devices every day, and they're embedded, like it's our watches, it's our smart home devices, our TV, or even our phones, our tablets, our laptops. They're continuously collecting our data to give us a better experience, to make better guesses about what we want. So there's everything around us that is gathering information and learning things from them. Now, naturally, we'll have this concern of, okay, if I'm giving away all this information, what about my privacy? What can people infer from this information? So this is how privacy fits into the context, that there are people gathering my information. They're sending it to this cloud or to a server to have some process run, learn from it, or even just give me a service, not maybe learn from it. And what is happening to my data when it's sent to a third party, when someone else is using it? So this is the main concern that we have. And I'm going to first talk about some famous incidents. So at very early stages, people used to think that anonymization would work. If I gather information from people and remove their IDs, then you should not be able to infer who was in the data set, what happened to their data, and which data belongs to whom. So it should be okay. But it's been proven time and again that this doesn't work. And the most famous incident was with the Netflix. And what happened was that Netflix in 2008, they released a data set of their users and the movies that they liked and the shows that they liked. And they removed their IDs and their zip codes and some personal identifiers. And they released it to public so that people could come up with better recommender systems. And it was kind of like a competition. This was called the Netflix Prize. And what happened was that I think in like less than a week, researchers were able to take this data set, and they also took the IMDb data set that is open to everyone, and they could figure out every single person, and they could figure out who has contributed to what data and what movies, and they could just kind of de-anonymize all the data. There have been many similar incidents, from some medical data in Washington State, Washington D.C., people were able to figure out I think some information about the governor and like what is his medical status. So this has happened a lot of times where data was released without the identifiers, and there were people who were able to, using some correlated types of information or some other data sets, they were able to figure out the people who had contributed. So anonymization alone just doesn't work.
Yeah, I can see that.
Yeah. I mean, you would expect that. But now, apart from that was just about gathering information. Assume that we are not releasing the information. We are releasing models. So we're taking people's training data. We're taking the data that they have contributed to a data set. We're training a model with it, and then we're releasing that model to the public. So we're not going to release the data set. And you would like assume that, okay, this is not still really good, but it might be better. But again, it's been shown that there are many privacy risks in this scheme too. So if you're releasing a model that was trained with some data, there have been many attacks called model inversion attacks or membership inference attacks, where attackers were able to figure out some data instances that had contributed to the data set, to the training data set of that model. So they could figure out whether this particular person was in a training set. And this is very risky in specifically medical settings, like you have a database of people who have diabetes or they have HIV. And if you figure out Alice is in the training data set, then you can infer that Alice has this disease. So it's giving away Alice's private information. And also sometimes there's this famous attack in 2015 that researchers were able to take a warfarin dosage model that would get your information and would prescribe warfarin to you. They could only take the output of this, like the dosage that was given to you, and then they could reverse engineer the model and get the person's private genetic information and private genome data. So they were able to, sorry. Yes.
That was terrifying, sorry, yeah.
Yes, it's really scary. And they were able to do it. So we can see that models, and this is mostly kind of attributed to the fact that models can memorize data. And from that, we are able to extract a lot of information about the people who have contributed to it. And another type of attack that you're seeing here is that when you have ML as a service, so there is this online provider that tells you that, okay, give me your data, I will train a model for you, and I promise, like, I'm not taking your data, I will train a model, and then I will give you this model, I will give you API access to the model so that you can just use it. And it's because, like, many times it's really hard to train an ML model or find a suitable model for people who are not, like, they don't have CS backgrounds, so many people use these ML as services. And it's been shown that using a term very similar to a normal regularizer, so without the people who want the model understanding it, they can add something that makes the model memorize even more. It kind of encodes the data in the model, and then from simple outputs, from like the last layer of the model, they can decode data and get images or get whatever data has contributed back. And here in this slide, that's what you're seeing. So the first row is like the actual training data, and then the other rows are data retrieved from the model. So it's like you feed a kind of like a dummy input to the model, and then it gives you an output, and you can decode it, and you can get the actual images. So wow. This is also kind of scary, but there are so many examples like this. There are so many papers. It's not just like one incident. So we should be really careful when we're training models and we're dealing with people's data. Okay. Yeah. So if we have any questions till this part, I would be glad to answer them now. If there are no questions, then I'll move on to that.
Yeah. For now we don't have
Okay.
Yeah. For now we don't have questions for this part, but probably later on. So please submit your questions in the comments so that we can answer them later. Thank you.
Yeah. Thank you. So let's look at the timeline here. What I'm trying to show in this image is to kind of show the progress of machine learning methods and also privacy preserving methods. So the first efforts for preserving privacy, they go way back. Like they start from where we started to like put locks on our doors and like put curtains on our windows. So it's like an old thing. Privacy is not really new. but more rigorous privacy guarantees for data aggregation and collection, they go back to 2002 and 2006, when researchers were trying to gather information and learn a statistically meaningful trends from the data, while at the same time not giving away people's information. So the most famous thing that people are using it today is differential privacy that came out in 2006. But before that, there was something called K-anonymity. What K-anonymity did, it was an anonymization method that has more rigorous guarantees, so it's not just like removing identifiers. It makes sure that in each data set, there are at least K similar entries. So even if you do get access to one entry, you don't know who it is because there are K-1 other people similar to it. It uses removing some information and making continuous data discrete so that data becomes similar. And it has a very strong guarantee, but the problem is that if the data is high dimensional, then it becomes a very hard problem to kind of figure out how to discretize data so that you can have the K similar people. After that, after 2006, when differential privacy was introduced, and what differential privacy basically tries to do in like simple words is that it tries to make sure that 1% effect on the output of whatever like algorithm or target task that you're running on the data, that 1% effect is bounded. So if I add Alice to my data set, and if I remove it, if I remove her, then the output of whatever algorithm I'm running on the data, I don't want it to have a huge change, so that if I know like what data exactly Alice is contributing. So it puts a bound on the effect that Alice or anyone has on the output of the algorithm. And it has some really good properties that I think it's like, if people have more questions, I'll explain more, but it basically, it kind of aggregates gracefully. So if you have multiple kind of differentially private algorithms running back to back, you don't lose a lot of privacy. They just add linearly. It scales linearly, basically. And it can also scale sublinearly with some like new methods, and not really new, but with some more complicated algorithms to use for the budget. And after that, in 2011 and 12, and actually starting from 2009, but mostly in 2011, there were papers coming out that made machine learning private. Like there are differentially private logistic regression, differentially private empirical risk minimization. All these papers came out around that time where machine learning was gaining more prominence. And there are so many papers. There are like over 600 papers on this. And after that, like 5 years after, in 2015 and 16, when deep neural networks were being used more, people started coming up with ways of making DNNs private. And by this, we mostly mean differentially private. And it involves like adding noise to the gradient updates, the most famous method that people use. It's called moments accountant. And I think the code for this one is also in the OpenMined toolset, if I'm not mistaken, or it's being deployed. I've seen it. But anyway, there are 900 papers on this. So it's like, it's a huge thing. A lot of people are working on it. Like, assume it came out in 2016, but it has around 900 citations so far. So it's like a really growing field. And then in 2000, so this goes for training deep neural networks. So what we mean here is that we have people's training data. We are trying to train a model, and we want to make sure that when the model is trained and we're releasing it, people are not able to extract a lot of information easily. But after that, and even around the same time, people were started to be concerned with, okay, assume that we're not trying to learn anything. We have this model, it's deployed, it's not learning, but I'm sending information to it so that it will give me a response. Like you call your, you say like, hey, Google, and then you like ask your question. And what happens is that normally Google learns from what you're saying, but let's assume that it's not going to learn. It's just going to answer your query. And you don't want it to collect your information, or you don't want it to infer more information from what you're sending. Or like if there's any background noise, or if there's someone talking to you, you don't want them to have access to this. So this is when concerns with like DNN inference privacy or like prediction time privacy came, where people are trying to like using noise addition, or mostly people use encryption. Using these methods, how can we make people's queries private, not the learning process? And how can we give them like this private response to their query? And this is like a less explored field. There are like 30, 40, there are more papers coming like basically every week, but it's less explored than the training kind of areas. And so we're saying that like technology and research, they're moving fast. Policymakers are also trying to keep up. We are having many new privacy policies like GDPR, which is the General Data Protection Regulation for Europe. And California has set CCPA in 2020, which is the California Consumer Privacy Act. And what these regulations try to do is basically they bound the kind of usage that entities can have from people's data. So I don't know if people who are in California, they've probably seen it. When you're opening sites since January, there is this button that you can push and say that, okay, I don't want you to sell my data. I've seen it on some websites. And this is kind of like you should have right to control your own data. There are some things called right to be forgotten that is in GDPR. It says that if you have even contributed to a data set, whenever you want to say I'm out, they should guarantee that you're forgotten. You're completely removed from like whatever data set that they have or whatever model that they have trained. And there's similar regulations in CCPA too. So again, if there are any questions so far, I think this would be a good time.
Yeah. Well, probably I would ask something like, for example, you talked about the prediction part, and what kind of like papers that are more like interesting kind of thing in this kind of field, so that like people learn more about it, because it's really interesting. It's a very like emerging field. So you have like, do you remember any?
Yeah, sure. So at the end of my presentation, and also I can share the link with you, I have prepared like a reading list of related papers for like each of these topics. And then there are also many surveys. But if I just want to say like some of the kind of famous works, there, as I said, there are three methods or like two methods roughly. So some of them are based on encryption, and there are many really good works on encryption. Most recent one is called Falcon, which is like the fastest one as well. There's Falcon, and then there's also so there's Gazelle, which is like kind of before this. It's like I think 2 or 3 years ago, but they're all very similar. And what they're doing is they're basically using secure multi-party computation. And this is the main kind of, it's completely private because your data gets encrypted. But the thing with the encryption mechanisms is that they're often slower, they're much slower than conventional execution. But more recent works, they're becoming really fast. So like, as I said, Falcon, it's like the fastest one. And this is like one line of work. And then there are these other lines of work that they're focusing on removing excessive information from queries. So assume you don't want to like have data encrypted. You want to have some clean, maybe censored data. And there are methods that use like information theoretic kind of tools and approaches. And for those, there's this relatively new paper called, it's called Censored and Fair Universal Representations. I will share these papers, but it's also kind of, it creates these, clean kind of representations. And I also have some papers that we use noise addition to kind of filter out excessive data and just send whatever important features are in there. So like if you're doing, there's this picture for like a smile detection. If you're doing smile detection, only your smile is being sent. So your image, your identity, your background, you're not sending any excessive information. So these are all like different approaches that have their, pros and cons. Like, as I said, encryption is like completely secure, but then it's slower, but you have like other methods, noise additions. It might not be completely secure, but then it's faster. So there's always trade-offs.
Yeah, there's always. Thank you very much for answering this question. Well, actually, we have another question. So, is why do you think the delivery private inference is a less explored problem, as you mentioned? Why is it less explored?
So I would say that maybe it's so like you start with bigger problems or like problems that, so people started like training was basically more important because you have all this people's private data, like you're using them in training sets, and there's so many attacks on this, so it kind of I think gained more attention because it's so much easier to like take out, extract data. But with kind of inference, I think people are more recently coming to see the problem. So maybe it wasn't as huge of a problem before as it is now. Like now we have more devices that are like, that you're like using, especially like, again, home devices or IoT devices, and they're all like sending queries, they're sending information to just answer a query. So I think maybe that's why it's becoming more of a thing right now. And before it wasn't that much of a concern, because maybe there weren't enough incidents, or like there are more attacks on the training part than there are on the inference part. I think maybe that's one reason.
Yeah, thank you.
Sure.
Thank you for answering that.
Sure.
Great.
So do we have more questions?
No more questions for now.
Okay, awesome. So
you can carry on.
So I think this is probably our last slide. So what I want to talk about here is privacy enhancing execution models. So there's kind of this, sometimes there's this like misunderstanding that there are like what methods bring privacy and what methods are privacy enhancing. And I think this distinction, we have to kind of make it more clear. And so there's some execution models that make applying privacy easier. They help privacy. They don't have any like guarantees on their own. They don't say that, okay, like your data is secure, or that we can give you the guarantee that this much information is leaking from your data, nothing more, or anything like that. They just make whatever execution model that you have right now more private, but they don't have guarantees. So one thing, the first and like the most famous one that is like gaining a lot of attention in research, and I think maybe also in industry, it's federated learning. That the basic kind of scheme is that, okay, the main problem comes from sending our data to some untrusted server or even like benign server. So why not bring the models to our devices, have some of the training like take place on the device, and I would only send the updates to this kind of central model, and then whatever server is there, it would aggregate these updates, it would average over them, and then apply these updates. So the benefits that it has is that I'm not sending my raw information, and the updates are getting they're getting averaged. So it's probably harder to kind of like infer who has sent what update. And also like I'm also doing my training. So the model gets updated, and then like this updated model is again deployed to devices, and this kind of thing keeps happening. So there is no like guarantee with this thing alone, but people usually use it with secure multi-party computation and like differential privacy to like give it guarantees, and it's like really getting explored these days. So it's a very important thing, and I think it's also being using in the Google Gboards, the keyboards that Google has. And yeah, so I think this is like a really interesting topic to work on. Just making it also like the main problems are the communication and kind of like making it faster and like giving it good guarantees. So yeah, this was federated learning. There's also this other scheme called the split learning. So what the split learning does, it's also been used in like other kind of aspects, but split learning means you split the neural network kind of, I don't know if it's vertically or horizontally, it depends on how you look at it, but you split it from the middle. And as opposed to like having different neural networks and different devices, here you're just cutting the network. You're executing the first part on the edge device, and then you're sending intermediate representation instead of sending the raw image. So intermediate representations in neural networks, they usually carry less information. So you're definitely sending less information, but you're still sending something. So again, there's no guarantee, but it's better than sending the raw information. So it's privacy enhancing. Again, like we have a paper that we have used this, and we have used a noise addition scheme to kind of make it more private. But there's no like guarantees alone. And finally, there are trusted execution environments. These are more, they're deployed on CPUs, and it's like this environment that you can have your code run in there, and you can be sure of integrity and confidentiality. But the problem is the whole process of getting information to these enclaves and like running your code and then getting it back, that has sometimes caused problems, because it's hard to kind of send your data safely and then get the result back. And there have been some side channel attacks on these environments. And also another problem is that like even if you have a completely secure, like a good TEE, they are only deployed on CPUs right now. The GPU versions are not kind of production ready, and they have like a lot of problems. So they're slow right now. Like we cannot run machine learning algorithms on them or like deep neural networks on them because we don't have them for GPUs yet. So yeah, that's the problem. So again, we have like privacy enhancing methods, but they're not all like, they don't have guarantees, or they're not like always perfect, and nothing is perfect ever. So yeah.
Exactly, nothing is perfect. So before we, yeah, you were saying something else?
No, I'm actually done, and I can like share a paper list kind of thing for people who want to read more on this. Yeah.
Cool. So yeah, before perhaps we can answer some questions that we have.
Sure.
So the first one is like, even in federated learning, could updates like the gradients be used to learn something about the original data?
So yes, gradients, I think there are papers, I can't think of them right now, but you can infer information from gradients. So that is actually a thing. And like, that is why in the moments accountant thing that I mentioned, the paper for differentially private deep learning, they actually add noise to the gradients, because all of the effect of your data, it shows itself as gradients, right? It's not learning in any other way, it's only the gradients. So the information extraction, it basically goes back to the gradients. So we can still learn stuff. That's why they say that they average them, so that you don't know which gradient belongs to whom. But even like from averages, you can still kind of figure it out. If someone has like larger gradients, then you can kind of figure out who has contributed what. So one thing that they do, it's kind of like part of the secure multi-party computation scheme to make this work. I'm gonna like make a very simple example. It's not this simple, but assume that, okay, you want to like, you have gradients of one person and you have gradients of another person, and you don't want to send them raw, but you want to send them and you want to have their average. So what they do is like, you generate this random number, and it's like, I don't know, it's like 3. You add 3 to one person and you add -3 to the other. So you're adding this noise to each of them. But when you add them and you get the average, it's still the same. So you see, it kind of, the noise, it cancels itself out. So you don't have, you're not giving the actual gradient value to the servers, but you are doing the overall correct computation at the end. So that's kind of like, in simple words, how it works. But if we send raw gradients, then yes, you can infer information. Does that answer the question, or like, are there follow-up questions on this? Okay, so I think Amel's connection is a little weak right now. I'm gonna try and see the questions myself. And okay, so we have a question that says, what's your view on the trade-offs between federated learning, split learning, and TEEs? Okay. Oh, actually there. Okay. So the trade-offs, I think TEEs need some more work from our engineers on kind of like lower levels of the stack. So I'm not completely like, I don't have that much information on them. But between federated learning and split learning, I think it's really, really kind of dependent on what context we're talking about. So it might not be possible for all devices, for like all edge devices, to bring the full models to the device. So then a split learning would work better, because you only have the first few layers traded off on the edge device. And even if your edge device is not that capable, it can still do the first few layers. But with federated learning, if I'm not mistaken, you have to like bring most of the model. So I think it has kind of a higher strain on the device that you're using. So with phones, it's probably easier, because our phones have very like a strong CPUs, and also many of them have GPUs. But with smaller devices or like devices that are deployed in, I don't know, in like your fridge or, you know, like IoT devices, I think it's harder to bring the model. So then maybe split learning would work better. Okay, let me, oh, I think Amel is back. Hey. Okay, so I'm going to go on to another question. Where we centrally orchestrate the hyperparameters and bootstrap models for participating devices? What if we split the complete analytics pipeline and let the system preserve the privacy? I'm not sure I completely understand the question. Centrally orchestrate parameters and bootstrap models for participating devices. What if we split the complete analytics pipeline and let the system preserve privacy? What do you mean by letting the system? Hey, Amel, can you? Hi.
Hi back. Sorry.
It's okay. So I actually went on and read one question when you were gone.
Cool.
So I'm at Muhammad Habib's question right now. If you could kind of restate your last part of the question, because I don't exactly know what you mean, but by letting the system preserve the privacy, do you mean like privacy by design, or is that what you mean? Or like how? What is it? How is it related to federated learning? If you could maybe like, you know, clarify that I would be able to better understand your question. Okay, the next one, is there any research available against exploiting hardware? Oh my God, yes. There are so many researchers on hardware. So like one example that I can say is like a really famous attack for hardware. It's called cache telepathy. And what they do is that they use, you know, hardware cache. So it's kind of like a memory that you first like load some stuff to the cache and then you do your computation. And if you don't need it, you just put it in the cache because you might need it again. So there is this attack that what they do is from the cache information, they figure out model properties and even the model architecture. It's called cache telepathy. It's like one of the famous works in this field. And there are many other works, like in security, there are many side channel attacks that people use timings or like how much time it takes for a packet to get sent over the network, or like even like there are papers that use the temperature of your device to figure out information about your models. So there are many, like they're very interesting because they're like mostly physical sometimes. So I can like introduce some of them, but again, the most like well-known one would be cache telepathy for me.
Cool. There is okay. I'll carry on with the questions.
Yes.
Okay.
Yes,
So no, it's okay. Just to make it easier for you. So there is, how should I start learning about federated learning? Do you have like recommendations for any books?
So honestly, I'm not that much of a federated learning expert myself, but there are some really good surveys. There's this, I can put the link, I don't remember the name, but it's by Brandon McMahon and a whole number of other people. It's this famous federated learning survey. It's 120 pages and it has all the like all whatever you would need to know basically. And I think you could just have a look at that, see what parts of federated learning you're most interested in, and then, you know, go from there. But there are many other like great experts in OpenMined who worked federated learning. So I think, you know, if you like ask it in the Slack channels, there'll be people who might know some other more things than what I just said, the survey. Yeah.
Yeah. Cool. Thank you.
Actually, one good thing I just remembered is that there's this site called Slides Live, and it has talks from NeurIPS and ICML and previous conferences and workshops. And there was this workshop on federated learning in NeurIPS, and all the talks and all the videos and all the panels, they're all there. So that's a really great thing to start with.
Thanks for sharing.
Sure, yeah, I actually remember that I watched that myself, and it was really good. Yeah.
Cool. Thank you. Another question is, are you aware of any interesting research on privacy-preserving NLP?
Yes, actually. So I think if like based on what I've seen is that mostly the trend was first on like images, and I'm seeing some new papers for NLP and for text kind of tasks. And a famous one is called The Secret Sharer, and it's by Nicholas Carlini. And it's a really interesting paper because what they're trying to do is they're trying to show how much like models that they're working with text, how much they memorize. And like it's like they show that they can kind of learn this whole the debit card sequences, and they can like completely memorize your numbers and like what they memorize, and then they come up with this way of how to figure out what they're memorizing and how to kind of alleviate it. And they talk about like different mechanisms. So I think The Secret Share is like one of the go-to papers for that field. Yeah.
Cool, thank you. Okay, another question is, could you share some thoughts on why differential privacy is bad for fairness?
So this is actually, yes, this is a really good question. And so this came out, I think, with this year's, there was a NURBS paper this year that it was titled like differential privacy has disparate impact on like accuracy. And what they showed was that when you're applying differential privacy to your statistics, your model, if it was doing like 3% better on like some sensitive groups like females or males, if it was doing 3% better on males, now that you're applying differential privacy, the skew is 10%. So it's doing way worse on like the underrepresented groups. And this actually looks really bad for like when we have like race groups or ethnic groups, because normally like we have fewer samples. And if differential privacy is really like bad, it's like it has disparate effects on them, then for like more important like budget allocation things, we're going to have problems, because people who have less representation, then they're going to get trumped more. So one reason for this is that because what differential privacy basically does is that it's assuming a worst case, and it's adding noise based on that worst case to like hide personal information. And when we're adding like a given amount of noise to hide something, if the size of the population is smaller than that, then that population is basically going to be hidden with the noise. So if the noise is kind of like negative, it's going to like remove whatever was there. Or if it's positive, then it has greater impact on a smaller populations. So that's basically where it comes from. It's the fact that you're adding the same noise to people who are like less represented, and the same noise to more people. So this is where it comes from. Yeah, and we're actually like in OpenMined, we have this research project that we're trying to kind of measure this in like broader data sets and in other kind of contexts, and then see the effects. So yeah, that's actually a very good question.
Cool. So another question is, what is the future of federated machine learning in healthcare? And another question is how much interpretability is involved in federated learning? So perhaps like let's divide it into what's the future of federated learning in healthcare as a first question.
So again, I'm not that much of a federated learning expert, but I think it would be a really good thing to have it, like, if you can have the privacy and if you can also have the usability. But the thing is, like in healthcare, it's very tricky, like we cannot just deploy any model and like do whatever we want, because it's people's personal data. But I think we actually have a project on federated learning for healthcare in OpenMined projects. But I think I would be glad to see it work, but I don't have like an expert kind of opinion for that. Sorry.
Yeah, no, it's okay. Thank you for answering. Well, the other question is how much interpretability is involved in federated learning, but I'm not sure.
So I'm not. So the thing is, like, interpretability goes back to the underlying model. So federated learning, it's just kind of a scheme. It's not like, it's not a training algorithm that would, that you're applying it. You're applying this like privacy enhancing scheme on whatever models you have deployed or you're using. So I wouldn't really like know if it has an impact on interpretability, but generally speaking, like from interpretability point, it's that mostly smaller models are more interpretable, like a small linear regression models, a small decision tree models, they're interpretable. But when it comes to deep learning, it's much, much harder to get interpretability, and there are not good metrics. So there are some methods there's this most famous one is called Lime. But then again, we don't really have metrics to measure how interpretable a model is. It's only some graphics and pictures that people put, and then they compare. So there's still a long way to go in interpretability, I think, yeah.
Cool, thank you for answering that. So another question is, what are the initial conditions you expect to see when quantum computing, neuromorphics, and differential privacy begin to intersect?
So I mean, but do you mean like post-quantum kind of like that, or?
I'm not sure. I'm not sure. Perhaps like they're combined together. If they're combined together or something, do you have like I don't know, initial conditions? Do you think like, yeah?
Yeah. So yeah, it's a little vague, but like I assume like what you mean is like if we have quantum computing, do these methods still work? So the thing is, like about differential privacy, it's that every time. So differential privacy is basically adding this noise, right? And if you make many queries, each time that you're making a query, you're exhausting your budget. So eventually, if your epsilon is not that small, like after 10 queries, you might be able to figure out the answer. So they're usually bound queries. So that doesn't really have to do with like quantum computing. Like even right now, if you don't have a good epsilon, then your model would break. So it's not really that dependent on computation. It's more dependent on the number of queries and like the epsilon. But what is dependent on quantum computing, it's like encryption. That some encryption methods will fail to work, but right now they're like, so what's happening right now is that there are researchers, especially like I know at Microsoft, that are working on coming up with post-quantum encryption mechanisms. So, they're trying to like do stuff that won't even break with quantum computing. So we should wait and see what happens.
Yeah, hopefully. Okay. I think, well, there is other question like, is there any work on the explainability of privacy preserving NLP? Do you have any like idea?
Explainability of privacy preserving NLP. That's a specific thing. I don't know. I think, yeah, again, the closest thing that comes to my mind right now, there's secret sharer, and then there are some works by Vitaly Shmatikov. I think it's called something auditing something. I forgot the name, but they're also doing work on NLP and privacy, and I'm not sure if they have explainability in it though. But yeah, I think explainability on its own is a little underexplored. So I don't know if it's been like done for NLP. I'm not sure.
Yeah, cool. Thank you. Okay, I think we'll answer 2 more questions and then we'll go to the Q&A that we have prepared before. But so there is, are there any practical real-time application of federated learning, like apart from Gboard? Like, what do you think federated learning can be used in?
So I haven't seen anything else deployed, and with this Gboard, even like this was again at a Noobs workshop that like my Brandon McMahon was like talking about it, and like even when he got asked the question that like what is the epsilon, and he didn't answer it like what epsilon they're using for the Gboard. That everyone was like, it was funny. But anyway, I'm not sure if there are anything else that is deployed. But yeah, again, I'm not a federated learning expert. I'm not sure. I just know the Gboard. Sorry.
Okay, no problem. Another question is, what are some interesting projects you are working on yourself related to privacy AI?
So I'm working on something like intersection of interpretability and privacy. It's kind of like figuring out what features are important in an image and keeping them, and like with respect to the neural network. So like figure out what the neural network has learned, how the neural network is making its decision, and only keep the information that is related to that, and just get rid of everything else. That's one thing I'm working on. But with OpenMined, we have 2 really interesting projects that I'm involved with. And one of them is kind of intersection of fairness and differential privacy and privacy. We are kind of trying to go through and survey methods and see like what effects they have on fairness, and if we can actually have fairness and privacy together, and how that would work out. And we also have an interpretable image, medical imaging project that's also very interesting. And we're like trying to kind of make the task of segmentation more interpretable. So we'll see where that goes.
Cool. Thank you for answering.
Thanks.
Okay, so probably we'll try to have some interesting questions from the Slido part. And okay, there is an interesting one. How do you stay up to date on privacy research?
So that's actually very hard, and it can also be overwhelming if you really want to like stay up to date. But I say mostly Twitter, because Twitter is like really good. If you follow the right people, then tweets are like, I don't know how many characters there are, but it's like 3 lines. So you read it. If it's related, then you like save it to read it later. That I sometimes never do, but
yeah, nobody did that.
Yeah, but you can actually like see what's going on. So I think following the right people on Twitter really helps. And also apart from that, you can like follow people on Google Scholar and then get emails once they have new papers out. And I think OpenMined also like does really good blog posts that explore what's going on. So that's also something else.
Cool. Thank you. Okay, another question is, okay, do you have like any questions or suggestions or tricks to help women be pioneers in the tech field? Like, and it's the same question for the research field.
Yeah, so that's actually a good question. I would say that one important thing is like for women who are already in tech field or like they're already higher up, to support women and to kind of like give them confidence and empower them. I think that really helps, because when you're working somewhere that it's like mostly male dominant, you end up being intimidated sometimes, or like you feel that maybe like you sometimes end up losing your confidence basically. So it's really important for you to have like role models to see, okay, there's this person, like she has made it, so I can make it too. And also to just to like give support and receive support. I've seen that like that really helps. And it also really helps to just not be afraid to speak up for yourself and not be afraid of being wrong. And sometimes when you're like in developing countries, I'm from one, and we are kind of brought up with this yeah, we are brought up with this belief that women don't belong in tech, or like they're not qualified or they're not competent enough. And even if you don't believe it, it gets to you, it like gets to you unconsciously. So if you speak up, and if you're wrong just one time, you end up not speaking up again, because you think, okay, they were right, I'm not made for this. But that's not the case. Like everyone makes mistakes and you can do it. So I think that like having confidence and not being intimidated, it helps. It doesn't matter if you're wrong. Everyone is wrong once in a while.
Yeah.
So,
yeah, totally. Cool. And another question is, how did you start getting interested in privacy preserving machine learning?
So that's actually kind of funny. I have a computer architecture background, and like I used to do computer architecture, and like I have a I was a computer engineer actually in undergrad. But we were working on neural network quantization to make neural networks run faster and kind of have accuracy at the same time. And what happened was that it was really similar to adding noise to the weights, because when you're quantizing, you're making things noisy, but it's still, you're getting good accuracy. So we were like, okay, what if we like manually kind of inject this noise and, make sure that the accuracy stays the same? And what happens then? And then like we started playing around with like noise, and we started like injecting it in different layers to activation weights, and like one thing led to another, and then we realized, okay, we can really use this for privacy. And that's how I kind of and then like when I started doing it, I really felt so.
Yeah, you really like it. Cool. That's inspiring, really. Another question is, it seems like privacy budgeting is often measuring whole data sets at a time. What if there are 2 data sets which have somewhat overlapping groups of people?
So that's a very good question. So differential privacy, what it does is that it assumes kind of an independence in data. So if you have correlated data, and even with differential privacy, you have some leakage. So what is done in these cases, there is this other kind of framework. It's called pufferfish privacy. What pufferfish privacy does is that it kind of assumes a correlation. So it's you can like say that, okay, I don't want these two features to get related, or like I don't want these two to be indistinguishable from each other. And differential privacy is actually kind of an instantiation of pufferfish privacy. So if people are like working on kind of getting privacy for some features, I would really recommend looking at pufferfish privacy papers. Yeah.
Thank you.
Sure.
Cool to know. Okay, another question is, can you please explain inference privacy in 2 words?
Okay, this is maybe like a cliche, but if I'm only going to say like 2 words, it's kind of human right. So like, you know, you're sending your data to someone to like run a service for you, and you have the right to know what's happening to your data. And that's kind of what inference privacy is. You don't want people to get control over your data. So yeah, I think that's the case.
Cool, great, thank you. And what are the challenges for secure and private AI and fairness in AI, in your opinion?
So one challenge is, like, as I mentioned, there's this trade-off, and so like you have accuracy, you have privacy, and you also have computation. And what happens is that, okay, you want to do more privacy, you either end up imposing more computation, like you use encryption, or you end up losing accuracy, like you add noise, or like you do differential privacy. Or like if you want to have high accuracy, you know, they're always like, you can't have them all. And I think that's the main challenge. And with fairness, again, like as I said, if you use differential privacy, sometimes fairness gets trumped. So you have to, like, you know, you have to have
the balance.
Yeah.
Yeah, exactly. Okay, so another question is, any tips on how to build a good profile for machine learning PhD admission for those who don't have access to top faculty for prior research experience?
Mm-hmm. So there are people who do like research, independent research. There was this person who got a paper in ICLR this year, and he was doing independent research. I don't remember his name, but he wrote his story in a Medium blog. So I think if you search independent researcher ICLR, I think you're going to find him. And he explained like what he went through. Like he had to, like, you know, pay for his own devices, and you know, like find people to be willing to work with him, like, although he's an independent researcher. So I think that's a very inspiring story. But I think that even he had some kind of help and mentors. It gets more difficult if you're trying to do it completely alone, like if there's literally no one who is like willing to help you. And in that case, machine learning is becoming very competitive to like get into. But what I would suggest is trying to, like, there are so many data sets right now, and they're all like available publicly. And I think Google Colab gives you some free GPUs and free power, so you can like start kind of coming up with your own tasks, or like looking at papers and getting inspired, and just trying to do projects on your own. And there are always people who are like willing to help you. Like you can email researchers, like email as many as them like as you can, and someone is bound to answer and like give you some guidance. And I think that's like a good way to go.
Yeah, cool. Thank you for sharing.
Sure.
Okay, this is a very weird question. What was the first project that you did work on for privacy preserving machine learning? It was kind of interesting. Well, I think you talked about it.
Yeah, it was the noise thing. That it was kind of a long journey for me to like learn what privacy metrics are out there. I was completely clueless back then, so that was fun to just like figure out what people are using, what works, what doesn't work, and I made some mistakes, but yeah, it worked out.
Yeah, everyone does. Okay, yeah. So, do you have any thoughts on search ranking and search engines working on encrypted data that are more robust to statistical inference techniques?
Okay, that was very long. So, like, it was ranking.
Yeah. Okay. Okay. I'll do it again. So, your thoughts on search ranking and search engines working on encrypted data that are more robust to statistical inference techniques?
So I'm not sure if I've seen encryption being used for like page rankings. I know that like right now for like rankings and for recommender systems and similar things, the state of the art is like a paper that came out in NeurIPS. It uses a form of exponential mechanism. So they use differential privacy as far as I know. And what they do is called top K something like, and with they do a good privacy budgeting. And I know that like that's one of the famous papers. I don't know if they use encryption. So one thing is that with encryption is good for inference because you don't want to learn things. But if you want to learn information from something, learning from encrypted data is very hard. So there are like fewer papers. There are very few papers that use encryption for learning. Mostly people use differential privacy for learning because it's easier. Models are usually robust. So if you end up feeding them some noise when you're training, you don't lose as much accuracy. So I think that's the way to go, exponential mechanism. Yeah.
Yeah, cool. Thank you. Okay, and we'll finish this talk with this last question. So, what has been the biggest challenges you have encountered in this field? How did you overcome them?
So for me, because like I work with as I said, I like come from an computer architecture background, and like my advisor is also a computer architect. So my biggest problem was like I didn't have a sanity check. Like when I came up with an idea or like a solution, I wasn't sure if it really makes sense, you know, and there weren't many people who like I could ask, or especially like at the beginning. Then you start collaborating with people and things get easier. But I had to do a whole lot of reading myself, because again, like there was no one I would say like I want to do this and like they would tell me, okay, go explore this method. Nothing. So I had to like start reading everything like from the beginning. I had to like read some books, papers, and you know, it takes time, and it can be difficult, but at the end it's rewarding. So
yeah, totally. Thank you for joining us today. It was really amazing, great presentation. Everything was really clear. Thank you everyone for coming and joining us. You can find the AMA online after, and see you in the next AMA. Goodbye.
Bye. Thank you so much, everyone. Thanks.